Okay, let us finish this off. So this will be done quite quickly, but you can pause, etc. So in the first thing, we want to go from t from 0 down to 20. This drag, yeah. There we go. And we want to do the Euler predictors, and that's done. Now this one isn't defined because this is still messy, but I think this code is actually basically correct. So Heun is the previous value plus the step size, and then you average two slopes, one according to the previous point, that's the B2, and then one according to the Euler predictor, that's that one. So it shouldn't be B3, it should be C3. Yeah. And then we bring that down, maybe tidy it up a little bit there. And then there's no point plotting the Euler predictor. There you get it. Okay. Now, are there any other questions here that we should answer? I think I don't do the exercises, I just give you kind of answers for the exercises. So the terminal velocity is 62.64, and the question is, how do we know that? Now here it's not there yet. Maybe if we go a bit further, it keeps on growing. Let's so does it go up towards 62.64? Yes, it does. Now, how we do that is as follows. If we look at the differential equation, so this is the acceleration. So when the acceleration is 0, the velocity doesn't change anymore. So if you solve this equal to 0, you will find 62.64. Once the velocity reaches 62.64, it won't change anymore. You're at terminal velocity. The reason is the gravity force balances out the drag. So you've got the gravity pushing you, pulling you down, and the drag going against them, and they're balanced. The force is 0, so the acceleration is 0, so the change in velocity is 0. You're at a constant velocity at that stage in the limit. Okay, now we're going into VBA. So we would have started this in the previous. So I think I'm just going to develop this code that I have here. So setting up the sheet, I think, was deleting columns 1 and 2. I'm not going to print the predictor. I'm going to get rid of that. I might bring in this DBLV Euler a little bit later on. At the moment, I'm not going to do that. So the initial values, okay, so take these from this thing. So H DBL final time is equal to cells 2, it's column 6, and then C and M in the next two. So DBLC and DBLM. Now have I given everything an initial value? H, yes. So now I'm going to give do, print the current value, so print the time, print the velocity. Now I'll choose that, okay. Column, I will get back to that afterwards, I think. If you still have handy columns, could print exact solution. Yeah, I'll get back to that. Calculating the next value. So the next time is easy enough. DBLT is equal to DBLT plus DBLH. Now I better just put some stuff in here for these. Say 1, 1. What about the Euler predictor? So DBLV predictor. Now it's very important you don't jump off the predictor. That was a rough estimate we used for a moment. You jump off the DBLV plus the step size DBLH times, and we must find out our, what's the derivative? So it's G, it's up there somewhere. G minus C over M times V squared. G minus C over M times V squared. G minus, fix this obviously, times V squared. Okay. Okay, so the G is 9.81. The C is DBLC. and the M is dBl_m, and the V is dBl_v. Okay. Now here it's kind of messing around a bit, so if I want to do a square, I could maybe do dBl_v by dBl_v. That would certainly do the job. Okay. Now I need to do Heun's method. So Heun's method says dBl_v is equal to the previous dBl_v plus dBl_h times, now average out two slopes. Is according to the previous point, plus another one according to the Euler predicted. So I just have to change the V's to predicted. Xt value is done. Calculate V predictor, that's done. Calculate V, yeah, that's all good. Loop. So in a loop until the time is bigger than the final time. And very important, save before you run a new loop. Save. Now this is basically all we want to see, but you can go a bit further. Where's the button? Yeah, there. Save before you run, very important. Like, there's a good chance I've made an error in that code there. That looks pretty good. So what I can do now is if I delete that, insert. I can run this multiple times because I have I've set up the delete thing in it. Now what was the previous C? I think if we just get the previous figures, the ones we use, so we can just compare. So 0.225 and 90. And just maybe move it down a little there. That seems to have not given enough time. Now I'm looking at this. Now maybe what we have to do is just graph it again because it's not selecting everything. I'm surprised it didn't. And I'm not sure if that fixes it, so there might be a little issue there. Like, what if I go to time 40? Will it know what I want? No, it doesn't. So we might have to be careful there. I think one thing you could put in selecting it in the macro recorder. Maybe we'll just try that for a second. So what we're going to do is, in the this may or may not work. So let's just select calls. So just at the end, just do that. And will that pick it up? Stop the recorder. Go into the modules. There it is. This may or may not work. I'm going to put it at the very end. It should be call, select calls. Doesn't work. So say if I change back to 30, well, that's a bad choice, 20. Does it go back? It does. What if I go up to 40? No, it didn't do it. It's kind of annoying. Now you can put, it looks not a big deal because you can just reselect. You can, there's another way around it where you can put in a graph in the macro recorder that you input the graph. Now the problem is then if you run it multiple times, you get loads of graphs. Then you can find a way to delete the previous graphs and get around it, but it's not a massive deal as far as I'm concerned. Okay, now have we done all these? Yeah, we've done all these. Now the additional functionality, yeah, we did that, but it didn't really make much difference. Additional, we could compare. So what I'm actually going to compare is we're going to do the V exact and also yeah, so we're going to put in okay, we're going to do this and then we're going to look at this separately. Okay, so I'm going to go back to my macro record. I'm going to record a new macro because I'm going to put in V Euler, V exact here, and I'm going to call this V Heun so we can compare the three of them. So I should stop. Oh yeah, I haven't recorded yet. Okay, so this is new setup. So I want to select all this stuff. Delete, that's delete on the keyboard, not the right click. T, V Heun, V Euler. it's annoying, the code will capture that annoying bit, and then v exact, which might need a bit of help, and then stop the recorder. So if I go into the module, it's down here. So yeah, you see the messing around here. If we want, it doesn't really matter, but I could delete that. That would just tidy it up slightly. Okay, so call the new setup. I'm not going to bother with the selecting. Okay, so what we're going to do is we're going to have an Euler method as well. So that's dblv Euler. The dblv exact doesn't need to be a variable. Yeah, so dblv Euler should also start at 0. And now we're going to print Euler in column 3, cells int row 3 equal to dblv Euler. The t is the same, and we just have to do the dblv Euler is actually easier. It's just dblv Euler. Now this is a genuine all Euler, not Euler particular used for Heun, so it does jump off the Euler. And maybe it might make sense to put this down here. Times the slope. This is the slope, but it should be dblv Euler. I'm not sure why the squaring didn't work there, but maybe it works for you. It's probably just one of those weird things. So save this, and yeah, that looks good. I want to get the exact in there as well. Now the exact doesn't need a variable, it just needs a suitable printing. So cells int row 4. Now obviously most of the time when you do this you don't have the exact solution. Now it's here, it's this yoke. I'm going to pause and write this formula down. Actually I need to check, does it have hyperbolic tan as well? There's a workaround if it doesn't. I did this hyperbolic tan here, and I'm going to get it from worksheet.function. So that's anything that works in Excel. You can get it to work in VBA by doing worksheet.function. So the formula I've written down for myself, there's like a square root. Now there's also another square root inside the hyperbolic tan, and I don't think the t is supposed to be in it. So there's a slight typo there. So isn't square root SQR? Isn't it? I can't remember. Isn't it? So that's another example. So VBA SQR is square root, yeah. So square root, it's mg, so dBLM times g is 9.81 divided by dBLC times worksheet function dot tan, hyperbolic tan, and then SQR times something. I'm fairly sure the dBLT is out here. And then inside in the square root it looks like C, which is dBLC, times, now if this is wrong I might have to pause and find the correct formula, dBLM. This is additional stuff, I'm not too worried about this. Save this, give it a run, does it work? Looks pretty good. So now let's compare them, which should be a bit of crack. They're really close. So the issue here is about kind of the C and the M and the step size. If I make the step size a whole lot bigger, and maybe, yeah, then you're seeing differences. Maybe, I think if you, so this is C over M, so if you make the M smaller and make this bigger, you're going to see bigger differences. Yeah. So here you're seeing the Euler method, you're seeing actual oscillations. Then you can kind of play around with this and have a bit of crack. There's way too much time here anyway with these numbers. Yeah, so that's kind of cool. So that's a problem with the second derivative. Now Heun isn't doing too hot either, but if you reduce the step size, look what happens to the error in the Heun's method. It goes way smaller. In fairness, the Euler method error goes kind of small as well. So a bit of crack here, yeah. So that's about all the functionality you could put in there. Now we'll do the other thing separately. Now this is actually something for the week afterwards. But but this is really additional. So don't watch all this video, skip to the next bit if you want. Okay, so what I'm saying is we can, okay, let's do some things the same. So I want to put in the x as well as the volume, basically. So to kind of look ahead, now I won't put in all the comparisons and stuff, we'll just do txv. htmc, let's start with 0.1, 10, say 50.2, something like that. May as well do the macro recorder here. So set up. So this is the XV. Now this is not for this week. It's saying you could do this. I am going to need an additional height. So that'll be x0. We'll start at, let's say, 1,000 meters, whatever. Crap. So that macro recorder is crap now because I shouldn't have done that. So I'll go again, macro recorder. So set up X and V sheet. So I want to select all these, delete on the thing, T, X, V, and that's enough. View code into my module. That's this one here. I want to set this up. That's going to set that up. I want option explicit. I also want, just for my own sanity, I want these to be bold. I think it looks better. And I want to center everything. I think it looks better. Right. So we've got these systems of things. So as before, set up your variables. So dim dblt as double. That's times. Dim dbl x as double. Dim dblv as double. And this is, I'm going to have to go through this quite quickly. It's definitely additional stuff because I'm going to do double Euler on this. Yeah, dbl x predictor, dim dblv predictor. What else we got? Dim dblh as double. The thing above, document property. This thing above as double. I've got dim dbl final time as double. Dim dblm as double. Dim dblc as double. And they're going to be a loop, so I need dim int row as integer. Give all these initial values. dblt starting at 0. dblx is going to be taken off the worksheet. Now I'm just going to put it as 1, 1 for the time being. Where is it? It's over here. That's 8, so it's 2, 9. Row 2, column 9. We're going to start the dblv from 0. The predictors don't need initial values. dblh, cells row 2, column 5. dbl final time equals cells, there it is, 2, 6. And then it's M and C. dblm, so the cells M, dblc equals cells, it's in column 8. We also need to start the row off. Oh, so same setup. Define variables, give them initial values, and then your loop. So do. So our printing cells int row column 1 is the time. Cells int row column 2 is the displacement. Cells int row 3 equal to dblv. Okay. Now our next values. So dblt is equal to dblt plus dblh is the easy one. Now we have to do, this is, as I said, this is for the week after. So this is opposite or revision, whatever that is. We need dblx predictor and dblv predictor. So the dblx predictor is dblx plus dblh times the derivative of x is v. Right? dBLV then, predictor is dBLV, the previous V, plus dBLH times the derivative of V, which is G minus C over mV squared. I'm just going to write that G minus C over m times V squared. Okay, G is fine, that's 9.81. C is dBLC, m is dBLm. I must multiply this by V squared. Maybe it lets me do it. I don't know why it doesn't like that. I have no idea why it doesn't like it. I'm just going to do dBLV by it's just some stupid thing. Right, now I'm going to do Heun for x. So dBLx is equal to dBLx plus dBLH times 2 slopes divided by 2. And use dBLV predictor, we should dBLV first, plus dBLV predictor divided by 2. The slope of x is v. And then dBLV is equal to dBLV plus dBLH times, take 2 slopes and average them out. One slope, 2 slopes, average them out. So the previous one is the dBLV, and then the new one is dBLV predict. Put the row up by 1, and then loop until I'm going to have 2 conditions. The dBLT is bigger than dBL final time, or the x is negative. I have to be careful here, so I need to make I might have to change some signs around here actually. So we're starting with x as the height above, and when that gets bigger than, so I need the x to be decreasing. So what that means is I need down to be the positive direction, isn't it? No, down to be the negative, and that means that these signs need to be changed around. Look, this isn't a big deal, don't get too worried about this. Yeah, so that just means that if you think of down as negative, because we're going to go from a height of, like say a positive height, say 1,000, down to 0. So the velocity is going to have to be negative. And the direction of the velocity is negative. So down is negative. And down is the direction of the gravity, so that's why that should be negative. And then the drag is going up, which is actually positive. So this should work. Very important to save it because I wrote that quite fast. Very easy to make mistakes, but thankfully I've saved it. Cool. Now it's jumped too quickly, so now you could get rid of the final time if you wanted actually, and I will do that because with the x it's more natural to keep on going. The only thing is if it takes a long time, and it gets there in the end. Let's plot all of these. Now the thing about this, oh that's great and all, so here you're seeing the velocity, the scale doesn't work very well. You might be able to adjust it, but here's the person falling. The only problem with this is free fall with quadratic drag is, sure you can solve it exactly. Why would you do this? Okay, but anyway, there we go. Now in terms of the exercises, I think I'm going to leave the exercise at this time and just get the answer in there for you. Okay, that's enough for this.